The morning sky above the Philippine Sea erupted into a hellscape of tracer fire and steel. Lieutenant Commander Hiroshi Matsumoto gripped the controls of his Nakajima Ki-43 Hayabusa fighter, its engine screaming as he dove toward the massive American fleet below. Behind him, 17 other pilots of the Thunder Eagle Special Attack Corps followed in perfect formation, each man having already written his final letter home. What none of them knew as they plunged through the dawn mist was that they were about to encounter the most devastating anti-aircraft technology ever deployed in naval warfare. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. Aboard the destroyer USS Richardson, Chief Petty Officer Marcus Sullivan watched the incoming formation through his rangefinder. His hands moved with practiced precision across the firing controls of the ship's revolutionary Mk-47 rapid-fire anti-aircraft system. The weapon beside him represented 3 years of secret development and a technological leap that would redefine naval combat forever. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. Aboard the destroyer USS Richardson, Chief Petty Officer Marcus Sullivan watched the incoming formation through his rangefinder. His hands moved with practiced precision across the firing controls of the ship's revolutionary Mk-47 rapid-fire anti-aircraft system. The weapon beside him represented 3 years of secret development and a technological leap that would redefine naval combat forever. In the next 4 minutes, this single mounting would discharge more rounds than an entire World War I battleship fired in a day. The date was October 14, 1944. The place was 200 miles east of Luzon. And what happened next would demonstrate why the Japanese High Command's most desperate gamble would ultimately fail against American industrial might and engineering genius. The Thunder Eagle pilots had trained for this moment for exactly 14 days. Unlike their predecessors who had spent months mastering the art of aerial combat, these young men had been given just enough instruction to reach their targets and die effectively. Lieutenant Commander Matsumoto, at 23, was considered a veteran with his 89 hours of flight time. Most of his squadron had never flown more than 40 hours before being assigned to the special attack units. Their aircraft bore little resemblance to the legendary Zeros that had dominated Pacific skies 3 years earlier. These Hayabusa fighters were older, slower, and carried none of the sophisticated equipment that had made Japanese naval aviation formidable. Each plane had been stripped of unnecessary weight and armor, then loaded with a single 250-kilogram bomb welded directly to the fuselage. The pilots themselves carried no parachutes, no survival gear, and no possibility of return. The philosophical preparation had been intense. Each man had participated in the ritual sake ceremony the night before, receiving blessed headbands inscribed with rising sun symbols and ancient prayers. They had composed death poems in the traditional style, meditated on the honor of sacrificing themselves for the emperor, and said farewell to photographs of families they would never see again. The youngest pilot, Ensign Takeshi Yamamoto, was 19 years old and had volunteered after his older brother died in the Mariana Islands campaign. What drove these young men to such extreme measures was the mathematical reality facing Japan in late 1944. Conventional attacks against American task forces had achieved success rates below 3%. Experienced pilots who had fought since Pearl Harbor were dead, and their replacements lacked the training to engage American fighters on equal terms. The Kamikaze represented a desperate attempt to transform inexperienced pilots into precision weapons, trading one life and one obsolete aircraft for potentially hundreds of American casualties and millions of dollars in ship damage. The early results had seemed promising. During the initial kamikaze attacks in the Philippines, success rates had reached nearly 30%. Ships had been sunk, carrier flight decks cratered, and American morale shaken by an enemy willing to die with mechanical certainty. Japanese naval intelligence calculated that sustained kamikaze operations could inflict losses severe enough to force American negotiation rather than invasion of the home islands. But the Americans they faced on October 14th were not the same force that had struggled against kamikaze attacks just months earlier. Below the incoming Thunder Eagle formation lay Task Force 61, equipped with weapon systems that represented the cutting edge of American military technology. Every destroyer, cruiser, and escort carrier mounted the new rapid-fire anti-aircraft guns that could sustain rates of fire previously considered impossible. Chief Petty Officer Sullivan's Mk-47 mounting was one of 48 identical systems distributed throughout the task force. Each weapon consisted of twin 40mm barrels fed by an automated loading system that could cycle through ammunition at unprecedented speeds. The shells themselves were a new design, optimized for maximum lethality against aircraft while maintaining accuracy at extreme ranges of fire. More importantly, the entire system was integrated with radar-directed fire control that could track and engage multiple targets simultaneously. The technical achievement represented by these weapons was staggering. Traditional anti-aircraft guns required manual loading, individual target tracking, and significant time delays between shots. The Mk-47 eliminated every bottleneck through revolutionary engineering. An automated feed system moved shells from storage magazines to firing chambers without human intervention. Hydraulic targeting systems responded to radar inputs faster than any human gunner could react. Most critically, the synchronized twin barrels could maintain continuous fire for extended periods without overheating or mechanical failure. Development had begun in early 1942 at the Naval Weapons Station in Maryland, where a team of engineers led by Dr. Samuel Harrison faced seemingly impossible requirements. The Navy demanded a weapon that could fire 7,000 rounds per minute from each barrel while maintaining accuracy sufficient to hit maneuvering aircraft at ranges exceeding 4,000 yards. The ammunition had to be powerful enough to destroy enemy planes with single hits, yet light enough for rapid handling by automated systems. The breakthrough came through a combination of metallurgical advances and precision manufacturing techniques borrowed from the automotive industry. The barrels were constructed using a new steel alloy that could withstand the extreme heat generated by rapid fire. The ammunition feed utilized a belt system similar to machine gun designs but scaled up to handle the much larger 40mm shells. Most ingeniously, the entire mounting was designed as a modular system that could be manufactured in separate facilities and assembled at shipyards with minimal skilled labor. By October 1944, American factories were producing these systems at a rate that astonished even their designers. The Ford Motor Company alone had manufactured over 800 complete mountings, while General Motors produced the ammunition at a rate of 50,000 rounds per day. The integration of American industrial capacity with military requirements had created a production miracle that Japanese planners could never have anticipated. The contrast with Japanese anti-aircraft capabilities was absolute. Imperial Navy ships still relied primarily on the Type 96 25mm gun, a design that required manual loading and individual targeting. Japanese crews could achieve maximum rates of fire around 200 rounds per minute under optimal conditions, but accuracy fell dramatically beyond 1,500 yards. More critically, Japanese industry lacked the precision manufacturing capability to produce automated systems or the radar technology necessary for effective fire control. Lieutenant Commander Matsumoto began his final approach completely unaware of the technological revolution waiting below. His intelligence briefings had described American anti-aircraft fire as heavy but inaccurate, based on reports from earlier in the war. The tactical doctrine developed for kamikaze attacks assumed that high-speed, low-altitude approaches would minimize exposure to defensive fire, allowing at least half the attacking aircraft to reach their targets. This assumption was about to be tested against the reality of 14,000 rounds per minute directed by electronic fire control systems that could predict aircraft movements with mathematical precision. The young Japanese pilots diving toward Task Force 61 were not just facing superior firepower, they were confronting a fundamental transformation in the nature of naval warfare itself.
Aboard USS Richardson, Chief Sullivan watched his radar screen as the incoming aircraft resolved into individual contacts.
Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means the fire control computer automatically calculated range, bearing, and projected intercept points for each target. Red lights indicated optimal firing solutions, while mechanical linkages adjusted barrel elevation and traverse with mechanical precision. Sullivan's job was simply to authorize engagement and monitor system performance, while the automated weapons did what human gunners could never accomplish. The ammunition loaded in the Mk-47 mountings represented another technological leap. Each 40mm shell contained a small explosive charge designed to fragment into hundreds of steel pieces upon detonation. The shells were manufactured to tolerances measured in thousandths of an inch, ensuring consistent ballistic performance and maximum lethality. Unlike earlier anti-aircraft ammunition that relied on direct hits for effectiveness, these rounds created zones of destruction through which aircraft simply could not fly. Fire control radar operators throughout Task Force 61 tracked the incoming Kamikaze formation with growing confidence. The new systems could maintain locks on multiple targets while automatically prioritizing threats based on range and approach angle. Information was shared instantaneously between ships, creating a coordinated defensive network that could engage dozens of aircraft simultaneously. The Americans were not just technologically superior, they were fighting as an integrated system while their opponents attacked as individuals. As the Thunder Eagle formation descended through 8,000 feet, proximity alarms began sounding throughout the American fleet. But unlike earlier battles where crews would have rushed to battle stations with barely controlled panic, the sailors manning the new rapid-fire systems moved with calm professionalism. They had trained extensively with these weapons and understood their capabilities. More importantly, they had seen the test results that demonstrated what 14,000 rounds per minute could accomplish against attacking aircraft. The mathematical reality was overwhelming. Each Mk-47 mounting could put 467 rounds into the air every minute from each barrel. With 48 mountings distributed throughout the task force, the combined rate of fire exceeded 45,000 rounds per minute. Even if only one-third of these weapons could engage the incoming formation simultaneously, they would create a density of fire that no aircraft could survive. Lieutenant Commander Matsumoto checked his airspeed one final time as his formation approached the outer edge of American defensive fire. His engine temperature was rising, a common problem with the older aircraft pressed into kamikaze service, but he calculated sufficient performance to reach the target area. Behind him, his pilots maintained formation discipline despite knowing they were minutes from death. Each man focused on the massive American ships growing larger through their windscreens, unaware they were already within range of weapons that would redefine the concept of anti-aircraft defense. The stage was set for a confrontation that would determine whether Japanese desperation could overcome American technology. In the next few minutes, mathematical precision would meet human sacrifice in the most dramatic terms possible. The outcome would influence not just this single battle, but the entire trajectory of the Pacific War and the future development of naval warfare itself. Chief Petty Officer Sullivan placed his hand on the firing authorization switch and waited for the final range calculation. Around him, 47 other weapon systems prepared to demonstrate why American industrial might, applied to military problems with scientific precision, would prove unstoppable, even against enemies willing to die for victory. The Thunder Eagle pilots were about to discover that courage and determination, however admirable, could not overcome the reality of 14,000 rounds per minute guided by electronic intelligence and fired with mechanical precision. The morning sun climbed higher over the Philippine Sea, illuminating what would become one of the most one-sided engagements in naval aviation history. The first shells erupted from USS Richardson's Mk-47 mounting at exactly 0847 hours, creating twin streams of tracer fire that arced through the morning sky like deadly ribbons.
Chief Petty Officer Sullivan felt the deck vibrate beneath his feet as the automated loading system cycled through its first belt of ammunition, each shell departing the barrel with a distinctive crack that multiplied across the task force as other ships opened fire simultaneously. The sound was unlike anything heard in previous naval battles, a continuous roar that seemed to tear the very air apart. Lieutenant Commander Matsumoto saw the tracers rising toward his formation and felt his breath catch in his throat. The volume of fire was beyond anything described in his briefings. Instead of the scattered bursts of anti-aircraft fire that earlier kamikaze pilots have reported, the sky ahead filled with what appeared to be solid walls of exploding steel. The American ships below had become the centers of expanding domes of destruction, each pulse of gunfire creating new layers of lethal fragments through which no aircraft could hope to pass. The mathematical precision of the American fire control system became apparent within seconds. Rather than firing randomly into the sky, each mounting targeted specific aircraft with calculated leads. Radar operators aboard USS Lexington tracked the incoming formation while computers processed speed, altitude, and bearing data faster than any human could calculate. The information flowed instantaneously to every gun mounting in the task force, creating a coordinated response that treated the entire defensive network as a single weapon system. Ensign Yamamoto, flying on Matsumoto's left wing, watched in horror as the aircraft directly ahead of him simply disintegrated. One moment his squadron mate was there, engine steady and bomb secured beneath the fuselage. The next moment, nothing remained but scattered debris falling toward the ocean below. The young pilot had no time to process what he had witnessed, because streams of 40mm shells were already tracking toward his own aircraft with mechanical inevitability. The effectiveness of the new American ammunition became devastatingly clear as the engagement intensified. Each 40mm shell contained precisely 2.4 ounces of high explosive, designed to fragment into hundreds of razor-sharp pieces upon detonation. The shells were timed to explode at predetermined distances, creating spears of destruction approximately 60 feet in diameter. When fired at a rate of 7,000 rounds per minute from each barrel, these weapons transformed the airspace around Task Force 61 into an environment where aircraft survival became mathematically impossible. Dr. Samuel Harrison, the chief designer of the Mk-47 system, had calculated these effects during development testing at the Naval Proving Ground. His team had determined that sustained fire at maximum rate would create overlapping zones of destruction dense enough to guarantee hits on any aircraft within effective range. The theoretical mathematics were now being validated in the most dramatic fashion as Japanese aircraft encountered the reality of American engineering precision applied to military problems. Aboard the cruiser USS Portland, Lieutenant James Morrison commanded 6 Mk-47 mountings that formed the task force's primary defensive screen. His radar operators had divided the incoming kamikaze formation into sectors, assigning specific aircraft to individual gun mountings while maintaining overall coordination through the ship's Combat Information Center. The integration of multiple weapon systems under centralized control represented a revolutionary advancement in naval tactics that the Japanese had no equivalent to counter. Morrison watched his guns traverse smoothly to track their assigned targets, the hydraulic systems responding to radar inputs with precision measured in fractions of degrees. The automated ammunition handling eliminated the human delays that had limited earlier anti-aircraft weapons, allowing sustained fire at rates that would have been impossible with manual loading. Each mounting could maintain maximum rate of fire for over 8 minutes before requiring ammunition resupply, more than sufficient time to engage the largest kamikaze formations. The contrast with Japanese capabilities was becoming tragically apparent as the Thunder Eagle formation encountered defensive fire unlike anything their pilots had imagined possible. Japanese anti-aircraft doctrine assumed that attacking aircraft could fly through defensive fire by accepting casualties while maintaining formation discipline. This assumption had proven valid against conventional weapons that fired relatively few rounds and required significant time between shots for reloading and retargeting. Lieutenant Commander Matsumoto attempted to lead his remaining aircraft in an evasive maneuver designed to minimize exposure to anti-aircraft fire. The tactic had been developed based on combat reports from earlier kamikaze attacks that described American guns as slow to traverse and limited in rate of fire. As his aircraft banked to avoid a concentration of tracer fire, Matsumoto discovered that the American weapons tracked his movements with electronic precision, automatically adjusting their aim to intercept his new flight path.
The automated fire control systems aboard American ships eliminated the human factors that had previously limited anti-aircraft effectiveness. Traditional gunners required time to observe target movements, calculate new firing solutions, and manually adjust their weapons accordingly. The Mk-47 mountings received continuous updates from radar systems that predicted aircraft positions several seconds in advance, allowing the guns to fire at where targets would be rather than where they currently appeared. Ensign Yamamoto managed to survive the initial barrage through a combination of luck and the inherent inaccuracy that affected even the most sophisticated weapon systems. His aircraft had taken multiple fragment hits that damaged the engine cooling system and shattered the canopy, but the control surfaces remained functional enough for him to continue toward the American fleet. As he descended through 3,000 feet, Yamamoto could see individual ships clearly enough to select specific targets for his attack. The young pilot chose USS Richardson as his target, partly because the destroyer appeared to be generating the heaviest volume of fire and therefore represented the greatest threat to his surviving squadron mates. What Yamamoto could not know was that Richardson mounted 8 Mk-47 systems specifically configured for close-range defense, creating a final defensive barrier that incoming kamikaze aircraft had to penetrate before reaching their targets. Chief Petty Officer Sullivan tracked Yamamoto's approach through his optical sight, while the automated fire control system calculated the optimal intercept solution. The Japanese aircraft was diving at nearly 300 miles per hour, its damaged engine trailing smoke and coolant vapor that created a distinctive visual signature against the morning sky. Sullivan's weapons were loaded with a special high-velocity ammunition designed specifically for close-range engagement of fast-moving targets. The technical sophistication of American ammunition manufacturing became critical at this point in the engagement. Each shell was manufactured to tolerances that ensured consistent ballistic performance even under extreme conditions. The explosive charges were precisely calculated to provide maximum fragmentation while maintaining enough structural integrity to penetrate aircraft skin before detonating. Quality control procedures verified that every round met specifications that exceeded military standards by significant margins. Japanese aircraft construction, by contrast, had been simplified and lightened to maximize production numbers while conserving strategic materials. The Hayabusa fighters attacking Task Force 61 lacked armor protection around critical components and used aluminum alloys that provided minimal resistance to high explosive fragmentation. When American shells found their targets, the results were catastrophic for aircraft designed primarily for mass production rather than survival. Lieutenant Morrison observed the engagement from Portland's bridge while coordinating defensive fire from his 6 gun mountings. The integration of multiple weapon systems under unified control allowed his ship to create interlocking fields of fire that eliminated gaps through which attacking aircraft might penetrate. Each mounting fired on slightly different trajectories, ensuring that any aircraft attempting to reach Portland would encounter continuous defensive fire regardless of its approach angle. The ammunition expenditure was enormous by previous standards, but sustainable due to American industrial capacity. Each Mk-47 mounting carried 2,000 rounds in ready storage, with additional ammunition available from below-deck magazines through automated handling systems. Portland alone could sustain maximum rate of fire for over 15 minutes without human intervention, representing more firepower than entire squadrons of earlier anti-aircraft weapons. Ensign Yamamoto pressed his attack despite multiple hits that had damaged his aircraft's control systems and wounded him severely. Blood from fragment cuts obscured his vision, while damaged control cables made the aircraft increasingly difficult to maneuver. His engine was overheating rapidly, indicating that his cooling system had been completely destroyed by defensive fire. Still, he maintained course toward USS Richardson with the determination that characterized kamikaze pilots throughout the war.
At 800 yards range, Chief Petty Officer Sullivan's weapons achieved what the system had been designed to accomplish. A concentration of 6 40mm shells detonated simultaneously around Yamamoto's aircraft, creating overlapping fragmentation patterns that no aircraft could survive. The Japanese fighter disintegrated instantly, its bomb detonating harmlessly in midair rather than against an American ship. Yamamoto's sacrifice, like those of his squadron mates, achieved nothing beyond adding to the growing casualty statistics that would eventually convince Japanese leaders that kamikaze tactics were unsustainable. The broader tactical picture revealed the complete effectiveness of American defensive systems against even the most determined kamikaze attacks. Of the original 18 aircraft that had begun the attack, only 2 managed to approach close enough to individual ships to pose serious threats. Both were destroyed by close-range defensive fire before reaching their targets. The remaining 16 aircraft fell to the concentrated fire of weapon systems that could sustain rates of fire previously considered impossible in naval combat. Dr. Harrison's calculations had proven accurate under the most extreme combat conditions. The Mk-47 system had achieved its design goal of creating defensive fire dense enough to guarantee target destruction within effective range. The mathematical relationship between rate of fire, ammunition lethality, and target vulnerability had been validated through actual combat rather than theoretical analysis. American engineering precision has overcome Japanese determination through the simple expedient of making kamikaze attacks mathematically impossible to execute successfully. The psychological impact on surviving Japanese pilots who witnessed these engagements was profound and lasting. Previous kamikaze attacks had achieved success rates sufficient to justify continued operations. When success rates dropped below 10% due to improved American defenses, the entire strategic logic of suicide attacks collapsed. Young pilots who had accepted death as the price of meaningful military achievement found themselves facing certain death with no corresponding strategic benefit. Task Force 61 continued its mission without significant damage or casualties, demonstrating that American naval forces equipped with advanced defensive systems could operate with near impunity against even the most fanatical enemy tactics. The strategic implications were clear to both sides. Japan's last desperate gamble had failed against American technological superiority applied systematically to military problems. The industrial statistics that enabled this defensive success were staggering in scope and demonstrated American manufacturing capacity at its peak. Ford Motor Company alone had produced over 1,200 complete Mk-47 systems using assembly line techniques adapted from automotive production. General Motors manufactured ammunition at rates exceeding 100,000 rounds per day while maintaining quality control standards that ensured consistent performance under combat conditions. This massive industrial effort represented more than simple manufacturing capacity. The integration of private industry with military requirements created an organizational model that could adapt rapidly to tactical needs while maintaining production schedules that met strategic requirements. Japanese industry, devastated by strategic bombing and resource shortages, could produce nothing comparable to American defensive systems that incorporated the latest advances in metallurgy, electronics, and precision manufacturing. The human cost of Japanese kamikaze tactics became undeniably clear as the war progressed, and American defensive capabilities continued to improve. Young pilots like Ensign Yamamoto died in futile attacks against weapon systems specifically designed to defeat their tactics. Their deaths, while individually tragic, contributed nothing to Japan's strategic position and only accelerated the military defeat that was becoming inevitable by late 1944. American sailors manning the defensive systems recognized both the effectiveness of their weapons and the courage of their enemies. Chief Petty Officer Sullivan later recalled the mixed emotions of operating weapons so effective that enemy attacks became one-sided massacres. The mathematical precision of American fire control systems eliminated the uncertainty that had characterized earlier naval battles, replacing tactical skill with technological superiority that guaranteed outcomes regardless of enemy determination. The Thunder Eagle Special Attack Corps had ceased to exist as an effective fighting unit within 4 minutes of beginning its attack against Task Force 61. The mathematical reality of 14,000 rounds per minute directed by electronic fire control systems had proven stronger than human sacrifice guided by spiritual determination. American technology had defeated Japanese fanaticism through the simple expedient of creating defensive systems that made enemy success mathematically impossible to execute successfully. The psychological impact on surviving Japanese pilots who witnessed these engagements was profound and lasting. Previous kamikaze attacks had achieved success rates sufficient to justify continued operations, despite heavy losses. When success rates dropped below 10% due to improved American defenses, the entire strategic logic of suicide attacks collapsed. Young pilots who had accepted death as the price of meaningful military achievement found themselves facing certain death with no corresponding strategic benefit. Task Force 61 continued its mission without significant damage or casualties, demonstrating that American naval forces equipped with advanced defensive systems could operate with near impunity against even the most fanatical enemy tactics. The strategic implications were clear to both sides. Japan's last desperate gamble had failed against American technological superiority applied systematically to military problems. The industrial statistics that enabled this defensive success were staggering in scope and demonstrated American manufacturing capacity at its peak. Ford Motor Company alone had produced over 1,200 complete